Okay, welcome to Chapter 6. Chapter 6 is on probability. And so a lot of this chapter is conceptual in nature, and we really use this chapter to create a foundation that we are going to build upon as we move into inferential stats here. Which is what we're starting to work towards. So, you want to make sure that you have a pretty good understanding of probability. Um, there's few calculations, or there's not a lot of calculation in this particular chapter. It's basically just taking everything you already know and adding one step. But there is a little bit of additional information in the worksheet tutorials that are not here on the slides. That's conceptual, and you'll need it for your quizzes. So make sure that you pay close attention during the worksheet tutorial in this video. All right, let's dive in. So we're going to talk about probability today, and this slide is going to be of particular importance because there's some stuff on it that's going to be on, I think, like 4 out of 7 of the quizzes in the exam. So make sure you have this handy. I would screenshot it because I don't think I've updated my slides with the most recent version of this. So at any rate, just make sure you have this slide handy. Okay, so probability is the likelihood of a specific outcome occurring. And the reason that we use probability is so that we don't have to constantly repeat the experiment to make sure the same findings occur. We do replication. We want to repeat our experiments to make sure that the same findings occur. But what this is referring to is having to constantly. So that word constantly, if you were asked this on like a short answer question on a quiz, why do we use probability? Why do we speak in terms of probability rather than certainty? When you're writing your answer, that word constantly is so important in your answer, because otherwise you're implying that we don't need to repeat our experiments, but we do. What we're saying here is not that we don't need to repeat our experiments, but that we are not able to repeat them over and over and over and over until we get through the entire population, because just like, who has time for that, right? So rather than constantly repeating experiments to make sure the findings occur for everyone in the population, scientists make probability statements. And then the second reason is that we haven't tested the entire population, which we've talked about the reasons we can't test the entire population a lot. So since we haven't tested the entire population, we can never be certain that our findings are true for everyone. And then the third reason that we use probability is because participants have individual differences that cannot always be accounted for. So if I am doing a study and my research question is, does violent TV cause aggression? I might decide to put half of my participants in a group where they watch violent TV, and then I observe their behavior through like a two-way mirror for an hour. And then I have my other half of participants that are in the control group, and they just chill for an hour or watch a placebo like Barney or something. And then I watch them interact for an hour and see how many aggressive acts they do. So I count the number of aggressive acts during my observations of these two groups, and my hypothesis is the group that has watched the violent TV is going to have a higher number of aggressive acts than the group that watched Barney. However, I can't say that the only reason the people in the experimental group, or the people that, watched the violent TV, were more aggressive is because of that violent TV. I can't say that for certain. I can't say I've proven that. Even if I do find a significant difference between the scores in the group that watches violent TV versus the group that watches Barney, I'm not able to say I've proven my hypothesis. I can only say that what I have found is probably is true of my sample, and therefore it's probably true of the population. And so again, going back to number 3, the reason I can't say I have for sure found and proven my hypothesis, violent TV causes aggression for everyone for sure. Another reason for that, besides 1 and 2, but in addition to 1 and 2, is participants have individual differences that are not always accounted for. So a person could be sitting there, and as I'm just going through the instructions for the experiment, they could be looking at my face, and it's reminding them of like the 5th grade bully that used to call them names and make them feel terrible about themselves. And as they're just reliving all these traumas of their life, they're looking at my face, and it's reminding them of all this horrible stuff, and they're just getting more and more angry inside. And maybe they didn't pay attention to the violent TV at all, but instead they were just thinking of how much they hated my face the whole time. So it wouldn't be appropriate to say that violent TV caused aggression in that individual, because instead it was my face that caused the aggression in that individual. And that's an individual difference. I have no idea that that's going on inside that participant's head. They're just sitting there. I'm assuming they're paying attention in the same way everyone else is, but they're having this whole internal struggle that I don't even know about. So because of this individual difference that we can't always account for, things that are going on within a person, maybe they're on drugs, maybe their boyfriend or girlfriend broke up with them, whatever, we can never say that we've proven our hypothesis, because we can't always account for these individual differences. However, we do always acknowledge them in our statistics, because that's the right thing to do. So I'll show you how we do that coming up in the semester. At any rate, the criteria for using probability are the following. First, each specific event must have an equally likely outcome. For example, if I flip a coin, the probability of getting heads must be equal to getting tails, which it is with a coin. And then the next criteria for using probability is that the probability value, which we symbolize with a P, as you see here, assigned to each specific event must be equal to or greater than 0, or equal to or less than 1. So in other words, P values, or probability values, fall between 0 and 1. So it's a lot of 2 digits after the decimal. A p-value that's equal to 0 means the event cannot occur, and a p-value equal to 1 means it must occur. So no p-value can fall outside of these limits. You can't have a p-value. You could think of it as dollars if that helps. You can't have a p-value over $1. So p-values are all cents you can think of if that helps. Or in other words, it's impossible to have a p-value of like 1.5 or 2.3. All p-values have to fall between 0 and 1. And then the sum of the probabilities assigned to all specific events must equal 1. So again, with that coin flip, if I flip it, we could assume that half the time it's going to land on heads, which would be equal to a probability value of 0.50. And we could assume that half the time when we flip it, it would land on tails. And so again, that's going to equal a probability value of 0.50. And when we add those two probabilities together, we get 1. And so that's what this third criteria is referencing. Okay, so there's two main types of probability. There's the expected relative frequency and the subjective interpretation of probability. So for the first one, the expected relative frequency is the outcome you expect to get if you repeat an event a large number of times. So going back to that previous slide when we were talking about the coin flip, I would expect to get heads 50% of the time, and tails 50% of the time. Or in other words, I would expect to get heads 1 out of every 2 times, or half the time. And then there's subjective interpretation of probability, and this is how certain you are that a particular thing will happen, but it's subjective, so it's not based on any objective evidence. So in other words, it's just you going, there's a 95% chance that my favorite restaurant is open tonight. And maybe that's an informed guess, maybe you go there like a lot, and somehow you've paid attention to the patterns of when it's open and when it's closed, and you know that, barring a national emergency, this restaurant's going to stay open. So 95% is like an informed guess, but it's still a guess, and it's still your subjective interpretation or your subjective guess, not based on objective evidence. So in number 1, we talked about a couple different ways to represent the probability here. We said when you coin flip, you can expect to get heads 1 out of 2 times, or 1/2, or 50%. And so we're just going to kind of revisit that down here at the bottom of your screen where it says probabilities expressed as symbols. So there's a bunch of different ways to represent a p-value. For the worksheet coming up and your homework, you're going to be doing a lot of p-values as a decimal. In this class, that's kind of our go-to. So if you want to report a probability as a decimal, you're just going to give a value between 0 and 1. And so you would write p equals 0.50, for example. And this you would say verbally as an event will occur 50 times out of 100. For percentage, you would just write the value and then the percentage symbol like we've been doing, and you could verbally read this as an event will occur 50% of the time. If you wanted to report probabilities as a fraction, you could just do that, p equals 1/2, for example, and you would verbally state that as an event that will occur 1 out of every 2 times. Or you can use the less than sign, which is the whole point of this chapter and everything we're working up to, but we'll get to in chapter 7 and 8 is using the less than sign. So we're going to, in inferential stats, be using this bottom one here with presenting the p-value, giving a less than symbol a lot. So once we get to chapter 7 and 8, that's going to be kind of our go-to probability symbolic representation. But for now, I just want to introduce you to it. So using the less than sign, this is an example of p less than 0.05. And this means that the probability is less than 0.05. So we're going to use that in hypothesis testing. You'll see that coming up more. But for this chapter, we're going to work mostly with probabilities as decimals. So there's two different models for calculating probability. The first one we're going to talk about here called the classical model. And the classical model calculates probability before any observations are made. And to use the classical model, you have to assume that the alternative events are mutually exclusive. So only one can be the observed outcome. You can't flip a coin and get both heads and tails. And then they are collectively exhaustive. So that means that one of these outcomes must result. So when you flip a coin, it is collectively exhaustive because it's either going to land on heads or tails. One time I did have a student that asked, what if it lands on its side in a crack of a sidewalk? And to that student, I say that would be the outlier. But in most cases, it's going to land on either the heads or the tails. And the probability classical model requires that all outcomes have an equally likelihood of occurring. So in other words, when I flip that coin, it's just as equally likely to land on heads as it is to land on tails. So the way that you calculate through this is you need to get the possible successful outcomes and divide them by all possible outcomes. And that's how you'll use this classical model to calculate probability. And so, for example, the probability of getting a 3 or lower when rolling dice. So all possible outcomes would be a 1, a 2, or a 3, right? Because your goal is to get a 3 or lower. You roll the dice. If you get a 3 or lower, you win. Let's say $20. So here you go, big money. You roll the dice. If you get a 1, 2, or a 3, you would win. So possible successful outcomes are 3. But when you roll the dice, all possible outcomes, like what are all the options, what are all the numbers it could land on, are going to be, you could roll the dice and it lands on a 1, a 2, a 3, a 4, a 5, or a 6. So all possible outcomes is 6. So if I wanted to calculate the probability for this particular situation, I would take possible successful outcomes, which is 3. I roll a 1, 2, or 3 over all possible outcomes, which are 6 because it's a 6-sided die. So 3 out of 6 would give me a p-value equal to 0.50. If I wanted to calculate the probability of multiple outcomes, I would need to calculate them independently. So what I mean by that is, for example, let's say this time I want to know what's the probability of me rolling a 3 2 times in a row. And so if there are 6 sides to a die and I want to get a 3, then I would only have one possible successful outcome, and that's a 3, over all possible successful outcomes, which would be a 6 because they're 6 side of the die. But I'm going to do that twice. So if you look here at the asterisk, it says p equals 1 over 6. That's that 3 over 6 possible sides. And then again, another 1 over 6. That's the second time I roll that dice. What's the probability of me getting a 3? There's only one 3 on the dice over 6 possible numbers. So when I calculate through that, 1 over 6 equals 0.17, and then again 1 over 6 equals 0.17. I multiply them together and I would get 0.03. Okay, then we have the empirical model for calculating probability. This is the one that's used primarily in sports, and that's because with the empirical model we calculate after observations have been made. So we use this model when events are not equally likely. Let's say you used a loaded coin, and so it was weighted to land on heads. Like, let's just say you're a little cheater, you're a little con artist, and you're using a loaded coin, and it's weighted to land on heads. If that were the case, then the events would not be equally likely. It's not equally likely that it's going to land on tails as many times as heads if it's a weighted coin. And then for the empirical model, the events have to be mutually exclusive in order to be able to use it. So one coin can't land on heads and tails at the same time. And then finally, past observations are used to calculate future probability. So calculation assumes there have been a lot of past observations made. So in order to calculate probability using the empirical model, you take the number of past observations for an outcome over the total observations. So for example, I'm a Chargers fan. I don't know if I told you that. If I haven't, I'm sorry. It's not really something you want to publicize because they lose all the time. It's not the best being a Chargers fan. But they're my team. I'm loyal. So here we go with my Chargers example. What is the probability that on this third down, the Chargers will convert to a first down? So let's say that they have converted 4 third downs so far this game. Those would constitute your past observations. So they've done this event 4 times already in this game. But they've had 16 third down opportunities so far this game. So that's the total observations. So I would take my 4 past observations and divide it by the 16 total observations or total chances they have. And that would give me a probability value equal to 0.25. Or if I wanted to represent it as a percentage, I could say 25%. So that's the empirical model. And the most important thing here is that we calculate probability using this model after we already have observations. Okay, so the next thing we're going to talk about is the Gamblers Fallacy. So the Gamblers Fallacy is kind of funny. You see it a lot in real life. It's assuming that after a losing streak, the probability must swing the other way and a win will surely occur. So I see this a lot when I go to Vegas or used to go to Vegas, and there would be these people that would be, sitting at the same machine for 6 hours. And I would just be wondering, what are they doing there, But it must have been the Gambler's Fallacy. They just were worried if they got up, as soon as they got up, someone else would sit down and win because they'd been sitting there for 6 hours losing. Surely a win is on the way. However, that's just not how it works, because when you're doing a slot machine, the slot machine isn't aware of how many wins and losses you have. It doesn't have any deep personal connection to you. So it's not oh man, Susie's lost 78 times. Better give her a win. Don't want to hurt her self-esteem. It doesn't work like that. It's not a sentient being. So each event, each, spin of that wheel on the slot machine is independent of every other spin of that wheel on the slot machine. So each individual spin has no correlation with any other spin. It doesn't have anything to do with if you've won or lost so far, the outcome of this event. So the outcome of the previous event of spinning that wheel, whether you won or lost, has no effect on the next event. Okay, so let's talk about odds now. Probabilities state the likelihood that events will occur. Odds are a little darker. They state the likelihood an event will not occur. So for example, if a question asks, what is the likelihood of rolling a die and getting any number, the probability would be 1/6. If we were to convert that to odds, you would need to identify the number of sides of the die that won't come up and then count the number of the sides that would come up. So if the probability was 1/6, what that means is that there's one number that's going to get that person a win, but there are 5 numbers that are going to make that person lose, right? So the odds would be 5. There's 5 numbers on a die that you lose if you roll, to 1, the one number that you need to win. So to calculate from probability to odds, you use the formula there on the slide, P divided by 1 minus P. So for example, if you're given a p-value equal to 0.20, you would just plug that into that formula there and reduce the fraction. You're going to determine if you're going to write against or in favor by referring back to the p-value. So you could see this one under the first asterisk, so the example is p equals 0.20. If we convert that to odds, we're going to get 4/1. And so then we need to decide if we're going to say 4/1 against or 4/1 in favor. And so because that p-value is below 0.50, I would say that this is 4/1 against. Whereas if I look at the p-value in the second asterisk there, that equals 0.80. 0.80 is above 0.50, so I would write this as 4-to-1 in favor. So that is how you convert from probability to odds. Okay, so we've been talking about the normal distribution, z-scores, and probability, and so now we're going to kind of tie it all together. The normal curve allows us to make statements about probability. The percentages that we calculated with z-scores are the percentages that we can be using as our probability statements. In other words, calculations about the area between two scores, calculations about the area above or below a certain z-score. And also, we can convert our percentages to probability values really easily by just dividing them by 100. So that's that extra step I had mentioned earlier on in this lecture. You're going to be PSPing as you've been doing with one extra step of dividing by 100 to get that p-value. So that's a bulk of what we're going to be doing on our probability homework. But let me give you an example and then we'll do the tutorial. So on a normal distribution with a mean of 25 and a standard deviation equal to 2.42, what is the probability that any single score will fall above a raw score of 27? So you're going to need to PSP as you've been doing, and as you know, you can't PSP without a z, so the first step would be to calculate that z-score, and then you're going to look up the percentage from the mean to the z-score in table A. In this particular case, it's asking for the shaded area above the z-score. So you're just PSPing as normal. You got that z-score, you plotted it, and wants the shaded area above the z-score, so you're going to shade above, and then you're going to go to table A and look up that percentage. It's going to be the unshaded chunk from the mean to your z-score, because this is asking for the shaded chunk above your z-score, so you're going to have to subtract the percentage you find on table A from the half of the curve you're working with and get that chunk out of there, so that what's left over is just that chunk above your z-score. So in this example, that would be equal to 20.33%, and then you would need to convert that to probability just by dividing by 100 and then rounding correctly. So you would see that the answer here is a p-value equal to 0.20. Okay, so let's do the probability worksheet tutorial. I'll go ahead and grab that off Canvas if you haven't yet, and we'll do it together. Okay, this is the probability worksheet. So we're going to start with number 1, and it says a certain event occurs one time out of 6 due to chance. What is the probability of that event occurring? So the number of successful outcomes over all possible outcomes here is 1 successful outcome over all possible of 6. So 1 divided by 6 is how I am going to calculate this probability. So if I do 1 divided by 6, I get 0.1666 and so on. So I'm going to look at the third digit to decide what to do with the second digit after the decimal. And it's a 5 or higher. So I'm going to round the second digit after the decimal, the hundredths place, to a 7. So this is going to be p equals 0.17 with correct rounding, and that is the answer for number 1. A. 1b says, what are the odds against the event occurring? And so here we're going to take the number of times that the event didn't occur. So if it had 6 possible chances of occurring and occurred 1 time, then there's 5 times that it didn't occur. And so we would say that the odds against that event occurring are 5 that don't occur to the 1 time that it did occur. So we would say 5-to-1. And in this case, the odds are against, and the reason for that is because the p-value is less than less than 0.50. So we would say that it's 5-to-1 against. Also because, you know, it says right there in the word problem, against. Number 2, a given event occurs at a frequency of 65%. What is the probability that the event will occur? So to calculate through this, what we're going to do is take our 65% and convert it to a p-value. And so in order to do that, we're just going to take 65 and divide it by 100, and that is going to equal 0.65. So that's how we convert a percentage to a p-value. We just divide it by 100. And then, so the answer is P equals 0.65. And then for number 3, assume that a deck of 52 cards is well shuffled. What is the probability of selecting a single card, for example, the Ace of Hearts? So for this, since there are 52 possible successful outcomes and one successful outcome, we would do 1 over 52. And 1 over 52 is going to equal 0.019. So with correct rounding, the p-value here is going to be 0.02. And then for 3B, it says, what are the odds against selecting that single card? So I know that it's saying that one card was selected out of a possible 52. So that means the odds against selecting that one card out of 52 are 51 to 1. So in other words, there's 51 opportunities to get it wrong and only 1 opportunity to get it right. Whereas the probability says there's 1 opportunity out of 52 to get it right. So they say the same thing, just in different ways. 4, at a certain casino, there are a large number of slot machines. On every slot machine, there are 3 wheels that operate independently. And on each wheel, there is a series of 7 pictures of various kinds of fruit: an orange, a grape, a banana, and so on. 4A asks, what is the probability that on a single spin, of the wheel, 3 oranges will appear? So for this one, and actually for me, in most statistical word problems such as this, I have to visually kind of picture the scenario, and sometimes I even go as far as to draw it out. Actually, a lot of time I draw it out, but I'm not an artist. I wish I was. I really value art, but I don't have any talent. So please don't judge me too harshly, but I think it's important that you understand what this problem is asking for. So what it's saying is there are a large number of slot machines. On every slot machine, there are 3 wheels that operate independently. So let's draw those 3 wheels. So here we have our slot machine. Again, please, I know I'm not a good artist. It's gonna just get worse. I think at first you're gonna be like, hey, that's not so bad. Maybe she can draw, but then wait, just wait. Okay, so let's say this is the slot machine. Okay, now we're going to draw the 3 wheels. Okay, and you know how there's the wheels and then there's like the little spot in the middle that marks off where the items come up that, you're playing with. So it says each wheel has 7 fruits on it. So 1, 2, 3, 4, 5, 6, 7. Okay, so let me repeat that on these real quick. And then there are, each wheel has 7 types of fruit in various locations. So here we go. Strawberry. No, that's not a strawberry. That's an orange. Orange. Do a little dot. Yeah, that makes it an orange. Okay, that's good. Okay, cherries. Those are good. Cherries aren't bad. Okay, and then, oh wait, I forgot to put cherries over here. I'm just putting them randomly because that's how they would be. Watermelon. Little boop, boop, boop. Watermelon down here. Watermelon up here. Okay, what else? An apple. You could, fast forward through this if you just want to get to the end. I'm not gonna blame you. Okay, apple. What other fruit is out there? Grapes. 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 I think I never did a strawberry, huh? Okay, strawberry. I started to, but it turned out like an orange. Now it looks like a pizza with a popsicle stick coming out of it. I try so hard to be an artist. Okay, and one more fruit. What's another fruit? Pineapple. Oh my gosh. Pineapple. 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 All right, whatever. Okay, so what this problem is saying is that, or you have this slot machine and it has this these 3 wheels, and on each wheel are 7 different types of fruit. So when you pull the lever here and spin it, oh, I forgot to put the spot where the money comes out. You pull the lever and it spins. What is the probability that on a single spin of the wheel, 3 oranges will appear? So what is the probability that when I pull this, I'm going to get this orange, and this orange to all come up in this window? So that's what it's asking. It was a real long walk to get there, but we got there. Okay. So the way that we would calculate through this is actually by going 1 over 7 3 times, because there are 3 wheels that are operating independently. So on each wheel, there are 7 fruits and only 1 orange. So you're going to do 1 out of 7, and you're going to do that 3 separate times, basically. So if you convert those fractions into decimals, you're just going to get 0.14 times 0.14 times 0.14. And when you multiply those together, you're going to get 0.003. And so when we round in this class, that would turn the answer into P equals 0.00. So you don't have any chance of getting that. Okay, B, what is the probability that on a single spin of the wheel, no oranges will appear? So the same thing again, you're going to do this method of multiplying 3 times, but in this case that you're not going to get any oranges to pop up in here. So any other fruit, but just not 3 oranges. What's the probability of that? And so since there are 6 other types of fruit on each wheel, the way we would calculate it is 6 over 7, 3 times. 6 pieces of fruit that are not an orange out of 7 pieces of fruit. So when we do the division there, we get 0.86. So we would multiply 0.86 3 times for this one, and that would get us a p-value equal to 0.64. So P equals 0.64 for 4B. So for 5, it says when an event cannot occur, its probability value is 0. When an event must occur, its probability value is 1. And then for 7 and 8, I'm going to be teaching you a new concept here that's not discussed in lecture. So make sure you pay extra attention to 7 and 8. So 7 says on the WISC 4, the mean on the arithmetic subtest is 10 with a standard deviation of 3. What is the probability of selecting at random one person who scores above an 11 or another person who scores below an 8? So we're going to solve through this just like we normally would with our z-score. And so we know the motto for z-scores is that you cannot PSP without a z. And so what I have here is a mean of 10, it says, a standard deviation of 3, and then I have 2 raw scores. I have a score of 11 and a score of 8. So let me write those off to the side here. So I don't have a z, but I do have everything I need to convert this raw score into a z-score. So I am going to begin by converting each of these raw scores into a z-score. So I'm going to start with the raw score of 11. And so it's going to be the raw score of 11 minus the mean of 10 over the standard deviation. So you know this formula. It's just z equals x minus the mean over the standard deviation. So that's what I'm doing here. The raw score, x minus the mean over the standard deviation. And when I calculate through that, I get 0.33 for my z-score. So I'm going to plot 0.33 over here. I'm going to guesstimate that it'd be about right there. So this would be, the z-score of 0.33 would be equivalent to a raw score of 11 if I wanted to put z-scores and raw scores down there. But I have just z-scores. And then I'm going to convert my raw score of 8 to a z-score. So 8 minus 10 over 3 is going to give me a z-score of negative 0.67. So I'm going to put that on the left side of the mean since it's a negative. Okay, so I've plotted my first step of PSPing, and now I'm going to need to shade. So I need to look at the word problem for my keyword so I can know where to put my shading. And so it says for the raw score of 11, we're going to shade above. So we had converted a raw score of 11 to a z-score of 0.33. So we're going to shade above the 0.33. Okay, and then for the raw score of 8, we converted to a negative 0.67. It says to shade below. So we're going to shade over here. Okay, so it wants the probability of selecting these two scores. So it wants one final answer or one final value as our answer. And so we're going to have to end, even though we are starting with two raw scores, we're going to have to end up with one p-value. So I'm going to show you how to do that. So we've plotted and we've shaded. The next step is to get the percentages. So we're going to go to table A and get this percentage here from the mean to a z-score of 0.33. And when we look on table A, we're going to see that from the mean to a z-score of 0.33 is 12.93% of cases. But that's not actually the chunk that we want from this half of the curve. We want this shaded chunk here. So since we're working with this half of the curve and we want to just remove this unshaded chunk, we're going to subtract this unshaded chunk from this half of the curve. So 50% minus this unshaded chunk here, when we subtract that out, so when we take that out, what's left over is going to be just the shaded chunk. So we're going to subtract out 12.93% from this half of the curve, and that's going to leave us with 37.07%. So this half of the curve is 37.07%. Okay, and then we're going to do the other side of the curve, so we got to find out what this unshaded chunk is, even though we don't really care about it. We care about the shaded chunk. We're going to use it to get us the info we do need. So on table A, it says from the mean to a z-score of 0.67 is 24.86. And we're going to subtract this chunk we don't care about out of this half of the curve that we're working with. So that's what is left over is that shaded chunk right there in the curve. So I'm going to subtract out this blank chunk from half the curve. And that is going to give us 25.14%. 25.14% is this shaded chunk of the curve. So we have 25.14% and 37.07%. So we have two percentages, but this is asking for one p-value. So the question is, what do we do now with these two percentages? So at this point, we want to turn them both into p-values. So we're going to go ahead and take our percentages and convert them to p-values. So to do that, we just divide by 100. So I'm going to take 2.14% and divide it by 100. And that is going to give me a p-value equal to 0.25. Then I'm going to do the same thing for my other percentage. I'm going to convert it to a p-value. So I'm going to take 37.07% and divide it by 100. And that is going to give me a p-value equal to 0.37. Okay, so it's asking for probability, and I have my two probability or p-values, as we call them on the statistics streets. I have those calculated, and so now I just need to figure out what to do with the two of them to end up with one final probability. So what I'm going to do is look for this keyword here that says or. And when I see that keyword or, I'm just going to make a note that or means to add p-values. Or is telling you to add your p-values. Okay, so 0.25 plus 0.37 is going to give me a p-value equal to 0.62. So my final answer here is going to be p equals 0.62. So using that same data again, let's look at what happens when instead of, so you do everything just the same as you did above here. You'd have to, it's all the same data. you'd have to start by, taking those raw scores and converting them to z-scores like we did above, and you would get these same answers. Then you would plot them here and get these same answers, and then you would shade in the same spots, look up the percentages, do the appropriate calculations, get the p-values, and then now I'm going to have you stop. So let's just, for the sake of time, we've done the same stuff over again, and here we are at p equals 0.25 and p equals 0.37. So it's the same exact steps up till this point. The only thing different about step 8 from step 7 is this word and. So when I have the word or, I add my two p values together. When I have the word and, just like in the cases above, where we want to know what are the probability of getting this orange and this orange and this orange, and we're multiplying, we're going to do the same thing down here. So if I see the word and in reference to my p-values, it's telling me to multiply my p-values. So I'm going to take 0.25 times 0.25 times 0.37, and that is going to give me an answer of 0.09. So p equals 0.09 for number 8. Okay, so for the next page here, we're going to start with number 9, and it says the mean systolic blood pressure taken from the population of student nurses in a large metropolitan hospital was found to be 122 millimeters with a standard deviation of 7. What is the probability of selecting at random someone whose blood pressure is 130 or higher? So we're going to have to PSP our way through this to end up with our p-value or our probability. And so in order to get that p-value, I'm going to write a little answer line here so I know what I'm working towards. I'm going to have to start by just kind of assessing what data do I have. So I have a mean of 120. I have a standard deviation of 7. And I have a raw score of 130. So in order to get a p-value, I have to PSP. And in order to PSP, I need a z. So I'm going to convert my raw score to a z-score using my z-score formula, which is my raw score minus the mean of 120. So I have 130 minus 120 over the standard deviation of 7. And when I calculate through that, I am going to get a z-score that is equal to 1.43. And then now that I have my z-score, I'm going to go ahead and plot it. So 1.43 is a positive z-score, so I'm going to plot it to the right of the mean. And next I need to look at where to shade. So here I see the word higher, which is synonymous with the word above. So I'm going to shade above. Okay. So I've plotted, I've shaded, and now I need to get my percentage. And so table A tells me from the mean to a z-score of 1.43. Don't have a table that tells me above a z-score of 1.43. So since I only have table A that tells me from the mean to a z-score, I'm going to go ahead and get the percentage of this unshaded section, or this unshaded chunk that I don't actually care about. I'm just going to use it to get the answer I do care about. So the percentage of this unshaded chunk here is 42.36. So I found that in table A. And so what I need to do is get rid of this unshaded chunk from this half of the curve that we're working with, so that what is left over is just this shaded portion. So I'm going to subtract this unshaded chunk from 50. So I'm going to do 50% minus 42.36. And what is left over is going to be 7.64%. So that's telling me this shaded chunk here is 7.64%. So am I done? No, I'm not done, because it's not asking for a percentage, it's asking for a p-value. So in order to get a p-value, I need to take my percentage and I need to divide it by 100. So 7.64 divided by 100 is going to give me a p-value of 0.0764. So I'm going to look at the third digit to decide what to do with my second digit. And the third digit is higher than a 5, so I'm going to bump up my second digit one value to an 8. So my final answer is P equals 0.08 for number 9. Okay, number 10 says the mean on the Woodcock-Johnson test of cognitive ability is 100 with a standard deviation of 15. What is the probability of selecting at random someone who scores between 92 and 100? So again, I ask myself first, what am I solving for? And the answer is P. So the next question I would ask myself is, how do you get a p-value? And I would say, Devin, you can't get a p-value unless you PSP. So in order to PSP, I need a z. So let me see what values I have, and then I can start PSPing through this problem. So I have a mean of 100. I have a standard deviation of 15. And I have two z-scores, 92 and 110. So I have to convert both of those raw scores to z-scores before I can begin PSPing. So I'm going to do that now. So a z-score that has a raw score of 92 minus the mean of 100 over the standard deviation of 15 is going to give me a z-score equal to negative 0.53. So I'm going to plot that over here, negative 0.53. And then I'm going to convert my z-score of 110 minus the mean of 100 over the standard deviation of 15. And now, I'm expecting to get a positive z-score here because my raw score is bigger than my mean. So I'm expecting to get a value that's also going to be bigger than the z-score mean of 0, or positive on the right side of the curve. So if I calculate through this, I do in fact get a positive z-score, as I should. So it's just kind of like a way to check our work. We don't get a lot of those in stats, so it's nice to identify them. And then I've plotted, and then now I need to shade. So my keyword for shade here is between. So I'm going to shade between my z-scores. And then I'm going to go, so I've plotted, I've shaded, I need to go to table A to get these percentages here. So this percentage from the mean to a z-score of 0.67 is going to be equal to 24.86%. And this chunk here from the mean to a z-score of negative 0.53 is 20.19%. So now I have these two percentages, and I need to convert them to I need to convert them to probability. So in order to do that, I'm going to first turn them into p-values. So I'm going to do 20.19 divided by 100. And when I do that, I'm going to end up with 0.2019. So I'm just going to leave that at 0.20 since the third digit is a 1. And then I'm going to do my other percentage here, 24.86 divided by 100, and that is going to equal 0.25. So then I'm going to take these two values and add them together, 0.25 plus 0.20, and that is going to give me a p-value of 0.45. So my final answer here is 0.45. Okay, these two problems are also not discussed heavily on the slides. I mean, they're referenced and the concepts are referred to a lot, but just these specific kind of ways of working with the curve or these specific terms are not covered on the slides. So you'll need these here in your notes. So it says using the data in number 10, so the mean of 100 and the standard deviation of 15. Find the two raw scores which exclude the extreme 10% of the distribution. So the first thing that we need to identify is what are called the exclusion areas. And so exclusion areas are the areas that are in the tails of the curve. And the exclusion areas
can be defined by the statistician. So it could be the extreme 6% of the curve, or the extreme 9% of the curve, or the extreme 12% of the curve. But in this case, it's the extreme 10% of the curve that the statistician is identifying as being the exclusion area. So when I'm working with the exclusion area and I'm given the percentage, I just have to mentally make a note that I need to divide that percentage in two, because there's two tails of the curve and the curve is symmetrical. So when I divide it by 2, I'm going to get 2 equal halves, and I'm going to put those 2 equal halves on either sides of the tail. So I'm going to take my 10%, divide it by 2, get 5%, and put half on here to represent this exclusion area, and also half on here to represent this exclusion area. I can't just represent one or the other, I have to represent both. So I just take my total extreme area percentage and divide by 2 to represent both of my tails. What this particular question wants to know is, what are the raw scores that are right here on the curve that are marking off the exclusion area for this particular data set where they're saying it's 10% that they want to work with. So in order to find those two raw scores, we are going to need to have our raw score formula, right? So that's where I always start. What am I solving for? X and X. So to solve for that, I need my raw score formula, which is X equals Z times the standard deviation plus the mean. And so let me see which of these values are given to me in the word problem. I have no mention of a z-score. I have a standard deviation of 15, and I have a mean of 100. But I don't have a z-score. So how am I going to get a z-score is the question. And basically, the way I'm going to get a z-score is by looking up these percentiles in Table B. So the way I'm going to look up the percentiles in Table B is I'm going to first have to kind of identify on the curve, which percentile we're at here. So if I'm at 5% of the curve on the left side, that's going to be the 5th percentile. And if I'm at this exclusion area over here where I'm marking off the top 5%, then what I actually have is the 95th percentile, right? Because you have the 100th percentile would be here, 99th, 98th, 97th, 96th, 95th, and then so on and so forth down that way. So on the left side, the percentage is the percentile, and then on the right side, you have to subtract the percentage from 100, or the 100th percentile. So I have the 5th percentile and the 95th percentile. So now I can go to Table B and get the z-scores that are associated with these two percentiles. So Table B tells me that the z-score at the 95th percentile is equal to 1.65. And so since the curve is symmetrical, I know that the z-score at the 5th percentile is equal to negative 1.65. So now I have my two z-scores for my raw scores. So I'm able to go ahead and convert them to my raw scores using this formula here. So I have a z of negative 1.65 times my standard deviation of 15 plus my mean of 100. And that's going to give me the raw score that's at the 5th percentile, or the negative, or at the z-score that's equal to negative 1.65. So when I calculate through that, negative 1.65 times 15 is negative 24.75 plus 100 is going to equal 75.25. So one of my raw scores is 75.25. And then I have this other raw score here that I need to solve for using the same formula, the raw score at the 95th percentile. So that is going to be positive z-score of 1.65 times that standard deviation of 15 plus the mean of 100. And when I calculate through that, I am going to get 124.75. So in other words, the raw score that's here is 75.25, and the raw score that's here is 124.75. So now for this bottom portion, I'm going to need to find the two raw scores, which include the middlemost 80% of the distribution. So again, I'm going to find the raw score that marks off the middlemost 80% of the distribution. And so if I'm marking off the middlemost 80%, that leaves 20% left over. And so I'm going to divide up that 20% and put it on the tails of the curve. So 10% on the right side and 10% on the left side. And then I'm going to solve it just the same way I solved for the above slide. I am going to go to my table B to get my z-scores, and then I'm going to enter them into the raw score formula to get that raw score. So in order to do that, I need to identify what percentile this is marking off at. And so again, on the left side, you just take the percentile that's given there and turn it into a percentage. So it's going to be 10% is going to equal the 10th percentile. And then over here, you just take the percentage in the curve and subtract it from 100, and then what's left over is going to be your percentile. So this here is marking off the 90th percentile because 100 minus 10 is 90. Okay, so then I would go to table B. Let me get my table B. And I'm going to look up the 10th percentile, and it says that's negative 1.28. So I'm going to put that down here, z-score of negative 1.28. So that means, since the curve is symmetrical, that the 90th percentile is at a z-score of positive 1.28. And then I just go ahead and plug them into my raw score formula, which is, again, z times the standard deviation plus the mean. So the z here is negative 1.28 times that same standard deviation of 15 plus 100. When I calculate through that, I'm going to end up with a raw score of 80.8. I'm going to put the 0 there as a placeholder, just so I get in the habit of always putting 2 digits after the decimal. And then I'm going to calculate through it again, this time with the z-score at the 90th percentile. And so that's going to be positive 1.28 times 15 plus 100. And that equals 119.20. So the raw score here is going to be 1.19.20, and the raw score here is 80.80. Okay, so I forgot to tell you that this portion here that's shaded in the middle is called the inclusion area. That's where most of the scores are included. So it's called the inclusion. So the middlemost 80%, or the middlemost section, you know, that 80% could change to 90% or whatever, depending on how the statisticians defined it. But the shaded middle part is the inclusion area. And when the tails are shaded, we're talking about the exclusion area. So make sure you have those terms written down in your notes. Tails are shaded, exclusion area, middle of the curve is shaded. We call that the inclusion area. Okay, and that is it for this probability worksheet.
Okay, and that is it for Chapter 6. Thanks for listening. I'll talk to you on the next one. Have a great day.